So all of these keto, it's like a ketose to aldose, all of them function in the same way. I would say the tricky thing about them is knowing to deprotonate a carbon, not to deprotonate an oxygen. Because if you try to deprotonate the alcohol to initiate the reaction, what you would inevitably find is that you end up breaking the carbon-carbon bond, and we can't do that, right? Because the bond doesn't break. We're just shifting the position of electrons. So the tricky part in those isomerase reactions is to think about how to initiate it. Okay. All right. So ligases. Before we really dig into mechanism for ligases, what I want to focus in on really strongly reinforce is this idea of energy transfer, right? So in chemistry, in biology, in biochemistry, we regularly say that it's the hydrolysis of ATP that drives the reactions, right? Provides the power for reactions to happen. Okay, and this is definitely true. It is the hydrolysis of a phosphodiester bond in ATP that is the central energy currency for living systems. That's absolutely true. But what we can't do is over here in space, right? So standing right here, take ATP and hydrolyze that bond. That produces energy. And then over here, try to power a non-spontaneous reaction, right? The energy of hydrolysis of ATP has to be physically coupled to whatever endergonic process you're trying to power, right? So we can't just magically use this energy to do something. We have to couple that energy in a physical way, okay? And these ligase reactions are a really great way of thinking about how that works, okay? So what we're looking at here is a very simple fatty acid, okay? So this is a simple fatty acid that's, I don't want to use yellow. It is 3 carbons, so propanoic acid, okay? Sorry, it's 4 carbons, butanoic acid. And the idea is we are coupling it to coenzyme A. So we're making what's called a thioester, okay? This is a really, really, really common reaction in biochemistry. Coenzyme A is an incredibly important carrier molecule for carbon chains, okay? But the way this works, right, is you start with a carboxylic acid and you're coupling it to a thiol or a thiolate. And the general idea is the thiol kind of replaces that oxygen and you lose hydroxide, right? So we end up with a thioester. Okay, just thinking in basic chemistry ideas, this reaction is not spontaneous by itself, right? We are going from reactants that have resonance forms, which is a good thing, right? Whenever we have resonance, it means things are stable, and we're going to a product that doesn't have resonance. So enthalpically, this is not spontaneous. Entropically, this is not spontaneous. We are going from 2 things to 1 thing. We are creating order. That's not spontaneous. This reaction, the coupling of a carboxylic acid to a sulfur-containing molecule, a thiol, coenzyme A, happens all the time in biology, but it's not spontaneous by itself. Okay, it has to be coupled to something that is spontaneous. So in this case, we are coupling it to the hydrolysis of ATP. ATP gets hydrolyzed, in this case down to AMP and pyrophosphate. And when it's hydrolyzed, that produces energy. That energy can be harnessed and used to power the non-spontaneous process of ligating coenzyme A to this butanoic acid. Okay? So thinking mechanistically, right? So we're here now. How can ATP do it? Again, we can't just magically say ATP gets hydrolyzed to AMP and pyrophosphate. That produces energy. That energy is used to force these 2 molecules together. That doesn't happen. Okay? So take a few minutes to work through your activity and see how this happens. And this is a massively important theme that we see throughout the entire semester, throughout all endergonic reactions in biochemistry, is how does energy get harnessed from a spontaneous reaction to drive a non-spontaneous reaction? All right, so let's go ahead and work through this question.